Welcome to this explainer. Today, we're jumping right in to tackle a massive gap in the renewable energy sector. We're talking about the gap between complex, theoretical wind turbine engineering and the practical hands-on training tools your maintenance teams actually need out in the field. We'll be exploring the ACM SL Wind Turbine Training Suite, which is specifically built to drive down training costs while completely supercharging your team's technical knowledge. So if you're ready to understand exactly how we train professionals to handle one of nature's most powerful forces, you are in the right place. Let's get to it.
Okay, let's dive right into this core question. How do you train for a severe wind gust without risking the power grid? Because honestly, understanding how to safely manage unpredictable weather is the ultimate goal of modern wind energy engineering. Think about it for a second. A wind farm isn't just an isolated fan. It's a fundamental production unit, pumping power directly into the electrical transmission network. If a massive gust hits out of nowhere, you can't just let that sudden massive surge of kinetic energy blow out the grid. But how on earth do you train a technician to manage that exact high-stakes scenario without literally putting a multi-million-dollar turbine and the grid itself on the line?
Here is our quick roadmap for today's explainer. First, we'll look at the wind turbine tech evolution. Second, taming unpredictable wind gusts. Third, real-time training simulators. Fourth, mastering the DFIG system. And finally, number 5, advanced engineering tools. All right, Section 1, Wind Turbine Tech Evolution, Tracing the 5 Families. To really grasp why modern training has to be so complex, we've got to look at how the tech itself has completely escalated. We've moved away from the historical starting point of simple, fixed speed or stall models, right through to highly advanced variable speed systems like the DFIG and the full converter. What we're tracking here isn't just a timeline of bigger machines, it's a timeline of how we learn to capture the wind much more intelligently. Each era represents a huge leap in how the electrical generators behave and how their production curves adapt on the fly to changing wind speeds. Just look at the contrast between an entry-level active stall turbine and a modern DFIG system. You can see just how drastic this evolution really is. We've moved from simple, direct-to-grid mechanical setups that use basic squirrel cage generators, which, are incredibly robust but totally rigid and lack speed control, to what are essentially highly complex active power production plants. The DFIG, which actually happens to be the most installed turbine family worldwide right now, relies on incredibly advanced power electronics just to operate at those highly variable speeds. Moving on to Section 2, Taming Unpredictable Wind Gusts and Protecting the Grid. Now, having a super complex turbine is great, but it's only beneficial if it can actually survive out in the elements, right? So the crucial takeaway here is understanding exactly how these advanced systems handle the violent, totally unpredictable nature of the wind. Older, simpler models face a huge problem. A sudden gust transmits direct mechanical and electrical stress straight into the grid. But starting with the third family, rotor resistance control, engineers introduced variable winding resistance. And wow, this was a massive game changer. Instead of transmitting destructive force directly, modern turbines use their drivetrains as kinetic energy storage devices. They literally absorb the shock of a sudden gust by varying their rotation speed, totally preventing those destructive electrical spikes. So to optimize this whole variable speed process, modern turbines rely on something called MPPT, or maximum power point tracking. Think of this as the brain of the entire operation. It's an intelligent algorithm that continuously, and I mean continuously, adjusts the blade rotation to perfectly match the wind speed. This ensures that the turbine executes its operational curve flawlessly, adjusting the RPMs from cut-in speed, which is the bare minimum wind required to actually generate power, all the way up to nominal power. It extracts every possible joule of available energy without wasting a single drop. That brings us to Section 3, Real-Time Training Simulators and the ACM SL Learning Path. So with the tech theory out of the way, how do we actually train for this? Well, ACM SL builds a brilliantly structured learning path using real-time simulators that directly mirror the evolution we just talked about. They break down this massive engineering challenge into 3 highly logical steps. Instead of just throwing a trainee into the deep end with a modern DFIG, they offer a real-time simulator for each major evolutionary leap. You just install one 50-megabyte base package, and then you seamlessly add the simulators as your team progresses.
Your team kicks things off with Step 1, the 65 MB active stall simulator. Honestly, it's the absolute perfect entry point. It introduces all the foundational concepts used across literally every turbine family. Your technicians will master basic subsystems, learn the standard start and stop operational conditions, and get crucial hands-on experience with the squirrel cage induction generator and dual-speed operation. It essentially builds their essential vocabulary from the ground up.
Next up is Step 2, the Rotor Resistance Controlled Simulator. This one is a non-negotiable, mandatory stepping stone for technicians before they even think about touching a modern system. Why? Well, because this simulator specifically teaches them how to solve that massive problem of wind gusts. It allows them to interactively see exactly how variable rotor resistance allows the drivetrain to act as an energy storage device, absorbing all that kinetic energy safely. All right, Section 4, Mastering the DFIG System, the complex production plant.
And that perfectly sets the stage for the capstone of the suite. The DFIG is entirely defined by its back-to-back converter. This is a highly sophisticated piece of power electronics that literally doubles the feed. It connects directly to the asynchronous induction machine, the main generator, to compute and control its internal magnetic and electrical variables. This means the generator isn't just sitting there at the mercy of the grid's fixed conditions anymore. It can be actively managed for highly advanced grid interaction. Since this is the most widely installed turbine family out there globally, training on it is absolutely vital. The DFIG real-time simulator lets your team practice handling realistic wind gust scenarios right on these advanced components. And what's incredibly practical here is that ACM SL actually offers the simulator for both 50 Hz and 60 Hz power grids. That means your technicians can train on the exact frequency specifications of your specific regional network. Finally, Section 5, Advanced Engineering Tools, essentially X-ray vision for turbines. But what happens when things go really wrong and you need to analyze a catastrophic failure? ACM SL goes beyond standard training. They offer highly specialized engineering tools for wind energy training that essentially act like X-ray vision, peering right into the invisible forces at work inside the nacelle. The operational curve calculator helps engineers design the drivetrain and the MPPT algorithms. Meanwhile, the DFIG back-to-back application actually computes the invisible magnetic and electrical variables going on inside the main generator. Let's zoom in on that operational curve calculator for a second. This isn't just guesswork. It's actually built directly around a landmark 2008 reference paper published by the National Renewable Energy Lab. This tool evaluates blade type, blade length, synchronous speed, and gearbox ratios to help engineers flawlessly define the operating conditions and perfect those MPPT algorithms we were raving about earlier. Then we have the DFIG back-to-back application, which is an absolute must-have post-mortem analysis tool. Look, when a complex DFIG turbine fails, you need to know exactly why. This tool allows your engineers to compute exactly what technical demand or load was placed on the back-to-back converter right during the fault event. It reconstructs how the electrical components interacted under stress, which is absolutely vital for preventing future catastrophic failures. So, the big question, how do you actually get this into the hands of your maintenance team? Integrating these simulators, the comprehensive encrypted tutorials, which are available in English, Spanish, and French, by the way, and the power electronics flashcards into your curriculum is completely seamless. ACM SL grants an instant free 2-day evaluation license the very moment you launch the app, absolutely no credit card required. You can even poke around their wind farm SCADA simulator to understand how the entire farm communicates with the transmission network. We've traced the massive evolution from simple stall mechanics right up to ultra-complex power electronics, and we've seen how dedicated simulators and engineering apps allowed training teams to truly master these incredible machines. The tools to safely bridge the gap between abstract theory and crucial hands-on practice are literally waiting for you to download. So the real question is, are you ready to take control of the wind?